what is r equals 2 cos 3 theta? What does he look like? He's what kind of curve? What are you picturing? Are you picturing anything? Yeah, Tyler, it's what? Cardioid. Close. There's no plus or minus in this one, but we're harder. It's a rose curve, absolutely. Do you see the difference? Yeah. Absolutely. Good. Thank you for answering. I love your enthusiasm. It's a rose curve. In fact, it's an odd number in there next to theta, right? What do they look like? Like petals, right? Little petals, right? In fact, how many petals am I going to have? 3. How many petals? 3. Thank you, 3. Awesome. I'm going to have 3 petals. Beautiful, beautiful, beautiful. Not that that really matters. In fact, if I want to get a picture, I'll get a picture. But if you're looking for a picture, I look for a picture. I see that curve, and I see this picture. And I visualize what these tangent lines look like. You see 3 tangent lines? You see 3 tangent lines, don't you? Where's your 3 tangent lines? Oh, I should pull this up. We got 3 tangent lines. Let me put a picture up here. So one side, let's put a picture up. So let's go this one. Nope, let's go this one. This, does that go? Yeah. Nope, wrong one. This one, that goes there. Yeah. Rose curve, right? R equals cosine 2 cosine 3 theta. 2's expanding, cosine 3 theta. It's a rose curve with 3 petals. Yes, it is. And I want to find the tangent line at the pole. But we say, whoo, this is interesting. Well, my curve has a tangent line here, and it has a tangent line here, and it has a tangent line here. So I specifically want you to find the one when theta is pi over 6. Because when theta is pi over 6, the cosine, so when theta is pi over 6, I have that the cosine of pi over 2 is 0, which tells me that my r value is 0. So when theta is pi over 6, right? When theta, my angle, is pi over 6, then r2 cosine 3 theta becomes r cosine 2 cosine 3 pi over 6, which is just pi over 2. So I have r equals 2 times the cosine of pi over 2, which is just 0. I'm just telling you that when you're at the angle theta is pi over 6, you have a radius of 0. It means you're at the pole. I'm just making sure that you guys see that you are absolutely at the pole. That is one place where you are at the pole, is when you're at theta equals pi over 6. There are actually 3 places, so if you're bored, you could find the other 2 places, within your interval. The other thing is we're considering, because we're only going once around that unit circle, once around that curve, okay, your limit here you should see is 0 to pi. So theta ranges from 0 to pi. So the angles that we're talking about where you're hitting your tangent lines are 0 to pi over 6. So at theta equals pi over 6. R equals 2 cos 3 theta. I am checking to make sure r equals 0, which means the curve is passing through the pole at that point. That's my logic. I will pass through the pole when r is 0. So let me make sure that when I plug pi over 6 in for my angle, I definitely get r being 0, just to make sure everything's kosher and everything's good. So you guys are working through this equation, and you are getting the slope. And who's helping me out? What was the formula for slope? Just to remind me, what is our slope? Our slope is what? Tyler is. Oh yes. Oh yes. Oh, you got it. Hang on, you got it. You got my equation. You absolutely. Y minus y1 equals m times x minus x1. 100% is my equation. You got it. 1,000%. So that's my equation for my tangent line. And my slope, what's that? What's the slope? Acacia, it's dy dx, right? We don't even think about that too hard because we already have been so ingrained from Calculus 1 that the first derivative in Cartesian coordinates x and y, dy dx, gives me the slope of the tangent line in Cartesian coordinates. So when we're writing these equations of tangent lines, we're going to x's and y's. Oh my, we're going to x's and y's, right? Did I just say we're going to x's and y's? Tomas, what is x? X in terms of, x is what? X is r cosine theta, isn't it? So we have to remember, if we're going to x's and y's, then we have to be mindful of our conversion factors, right? And so x is r cosine theta, y is r sine theta, and then just warming up and remembering, so if we get dy dx, we have to take dy d theta over dx d theta, and then we have to replace r with what the curve is, and then we have to take the derivative, and you guys are going, and I'm looking to see if you match me. I'm going to wander. Let's see. Hang on. Let me put it here. Somebody check my work because I always make mistakes. So help me out here. So dy d theta. Whoa, Tina. First of all, we have to rewrite y. Y is r, which is 2 cos 3 theta times sine theta. And x is just 2 cos 3 theta. Oh, no, Tina. I'm just going to put that underneath because it's too messy up here. Let me erase this and put y is here and x is r, which is 2 cos 3 theta times cosine theta. So first thing you guys did was you replaced the r's with what r is, 2 cosine 3 theta. And then you said, oh, hello there, I have some products going on. So you guys should be applying the product rule for derivatives when you take your derivatives here. That's the second thing, right? So be careful. You're applying the product rule for derivatives because we got products going on. Derivative of the first times the second and all that good stuff. dy dx. Y is a function of theta. X is also a function of theta. So when we take the derivatives, we have to take each derivative separately, dy d theta, dx d theta, and then divide. So we've got dy d theta is... derivative of the first is going to be minus 6 sine 3 theta times sine theta. Plus, derivative of the second is cosine. 2 cosine 3 theta cosine theta. You guys are checking my work, right? And making sure I'm getting the same thing as you. Derivative of x, derivative of the first is going to give me minus 6 sine of 3 theta times the cosine of theta, plus derivative of the second is 2 cosine 3 theta sine theta, but I got to put a negative in front. So let me erase and put a negative in front. Okay, cool. Does that match you? Now, don't simplify. There's no need to simplify. We don't need to simplify at this point. Really, if we had to simplify, you have to factor out and cancel, and it doesn't look like anything's really going to simplify. So our next job is to actually say, okay, let's look right at theta equals pi over 6. So we're going to look at theta equals pi over 6. Let me put this on over here too. So at theta equals pi over 6, I have negative 6 sine 3 pi over 6 times the sine of pi over 6 plus 2 cos 3 pi over 6 times the cos of pi over 6. And if you guys have any questions, I am taking questions as well as writing things down so that you guys can ask, so that we leave here having questions answered, because that really helps when our questions get answered. Students ask questions. That's what you do. You discover, you learn, you create. Questions are good. So let's get those questions answered first before we move on. Who's got questions? Who's got questions? Am I matching your work? Is everybody looking good? I would not simplify here because it's really yucky and messy, but I will simplify here because it's really yucky and messy. But it's not too bad because we have to remember that we multiply our angles before we evaluate sines and cosines. So hopefully you guys see 3 pi over 6 as pi divided by 2 because 3 goes into 6. And 3 pi over 6 is actually pi over 2. And that's also true right here. And that's also true right here. So no questions. You guys have no questions. Now, Ben, this is where it gets nice. Did you see it got nice here? Yeah. Because cosine of pi over 2 is just 0. So this whole term drops out here. This is all 0 here. This is all 0 here. That whole term drops out. And sine pi over 2 is just 1. So this guy is just 1. And so when I put it together, I just get negative 6 times the sine of pi over 6 over negative 6 times the cosine, and I copied it wrong. You guys see I copied wrong. That's a pi over 6, right? Cosine pi over 6. Which is just, if I like to see it, tangent pi over 6. If I want to think of it that way, the derivative is just tangent pi over 6 because sine over cosine and the negative 6's in the front goes away. And at pi over 6, I don't know why I almost did it again. I did it this morning, messed that one up. Pi over 6 is right here at 30 degrees. And that point is the point square root 3 over 2, 1/2 if I'm linking on the unit circle. And the tangent is sine over cosine, or y over x, so 1/2 over the square root 3 over 2. And that's just 1 over the square root of 3. So are you guys getting slope? Did everybody get a slope of 1 over the square root of 3? Did you get it, Tim? Did you get it? Okay. So, yeah, Zach? Will we get the unit circle in the exam? Will you get the unit circle? Okay, so what do we got going here? Now, we have the slope of the tangent line, and then we get the equation. This tangent, so I'm just going to sketch this curve here quick, but you guys can see this curve right here on Desmos that I have pulled up. This curve has a tangent. Which tangent am I? Which tangent am I? There's 3 of them. 1 here, 1 here, 1 here. I'm the one with the positive slope, right? Which better make me this one right here. And where am I hitting? I'm hitting at the origin, 0, 0. So to write the equation of the line, it's really simple. It'll be y minus 0 times 1 over the square root of 3 times x minus 0. And let me type that in Desmos, and let's make sure that works. Y minus 0 equals 1 divided by square root of 3 times x minus 0. Perfect. Ooh, it didn't like my 0 because I typed a no. There we go. So we got one tangent, right? Oh, you can't see it. Hang on, let me show you my tangent. Left tangent. There we go. One tangent, right there. Okay, if we want to find all 3 tangent lines, I love that question. What would we do? I love that question. What would we do if we wanted to find all 3 tangent lines? Ty.
Would we have to change our theta?
We would have to change our theta. And how would I get my thetas? How would I get the other thetas other than using Desmos? Let's say I don't have Desmos and I want to use my brain. How would I get my other angles? How would I get them? What would I do? Yeah, James.
Since we know it makes a full loop at pi, can we assume that there's one at pi over 6, one at 3 pi over 6, and one at 5 pi over 6?
Oh, that's a good guess. That's a good guess because they all differ by
1/3.
1/3. Pi over 6, pi over 2, 5 pi over 6. Now they're not equal segments. But they are because I see. So you're thinking, okay, I don't know what you're thinking, but you're thinking these three here because this is 1/3, this is 1/3, and these two together make another third. And you could do it that way, 1,000%. That's absolutely correct. Those will be my things. But some people don't have that intuition. Some people can't visualize and see those three loops or those three places. So in that case, you can use good old algebra and thought process with trigonometry. And we did this last time as our warm-up. I don't know if you guys remember, but last time I said solve a trigonometric equation, and I said solve this equal to 0. Do you remember, kind of, if you look in your notes? So I was prepping you to say, where am I hitting the pole? Where does this equal 0? And so I would say, well, that equals 0. Cosine of what gives me 0? So I'll just go back over what we did last time. So we said that will be 0 when we have an angle in here that gives me a 0 value. So cosine of what equals 0? And we said, where's cosine 0, Derek? Do you know where cosine is 0? At what numbers? Just guess. Pi over 2? Give me another one. 3 pi over 2? Yeah. Yeah? And maybe 5 pi over 2? And maybe 5 pi over 2? So all the pi over 2's, right? And so if that's true, that means 3 theta would have to be pi over 2. So theta is pi over 6. 3 theta would have to be 3 pi over 2. And so that means theta is 3 pi over 6, which is pi over 2, right? And then 3 theta would have to be 5 pi over 2. So that means that theta is 5 pi over 6. So those guys would be the places, right? We talked about this last time. Do you guys remember doing this a little bit? I see some heads nodding. A little bit last time. So all we're doing is saying, where is this curve equal to 0? I like this. That's more intuitive, like more spatially, visually appealing to me. How can you, if you know one of them's at pi over 6, how can you make sure the rest is all divided equally up into 3 parts? So that's another way to look at it that way. But this will get you there with algebra, if you like algebra. When does cosine equal 0? Cosine equals 0 at pi over 2, 3 pi over 5, pi over 2. That means whatever this is inside has to equal those. And this kind of process will help you, so whether cosine is 3 theta or 7 theta or 5 theta, then you simply would just replace 5 theta, 3 theta, 7 theta down here and get your angles that way. Okay, any questions? Any other questions? So Ty, you asked that question. Do you see? So the 2 other places, and you would want to confirm, but if you tried pi over 2 and 5 pi over 6, it would give you, I bet, the other 2 tangent lines. Well, not I bet, I know. It will give you the other 2 tangent. Ready? Let's talk area. Let's talk area. So this is what I wonder. I wonder what makes the area of a polar curve. And when we talk about area related to polar curves, where am I talking? Am I talking area under it? What am I talking? What do you think I'm talking about? Tyler.
I'm talking about the area within the shape.
Yeah, I'm talking about the area within the shapes. Okay, because parametric curves they touch themselves often. I mean, like they cross over each other and stuff. So they connect, they intersect themselves. So we have to worry about the area inside. What makes it different when you talk about area in terms of polar coordinates versus rectangular. Now notice, I didn't even change him to polar coordinates. If I change this graph to polar, it gives me the exact same picture, right? It gives me the exact same picture. It's just a different reference. So what makes it different is the whole values that we're talking about. In a rectangular plane, what are we talking about? We're talking about x's and y's. In a polar plane, we're not. So I wonder what makes them different. So if I have a rectangular plane, and I'm looking in terms of x's and y's versus a polar plane, what's the big difference? When I'm in the polar plane, what are my variables? Or the ones that I'm looking and focusing on? R and theta, right? R and theta. And what is R? R is the distance from the pole, right? And so R would be this distance from the pole. And what is theta? Theta is the angle that gets there, right? But in the xy plane, if I have a function, and let's say I'm going from A to B in the xy plane, how did we get the area in the Cartesian system? How did we get that area? Let's look at that first. What did we do? Do you guys remember from Calc 1 what you did? Zach, do you want to describe for me how you get area in the xy plane? Where did it all come from?
You just do the limit from A to B.
Oh, we do a limit. We do an integral. But where did it start? It started with something like, what did we do? We broke up this area into what? Do you guys remember with the Riemann sums? Gwen, what was it? Do you remember? Yes, you do. Riemann sums. Yes, you do. As soon as I put it up here, you're going to be ready. What was it? It was rectangles. Yeah? Yeah. Rectangles. Do you remember doing this? You can tell me no, I don't ever remember doing this. I am having breakfast with Professor Montgomery on Thursday, so everybody remembers this, right, guys? Everybody. Do you guys remember the rectangles, right? The rectangles. So we approximated an area with rectangles. Okay. So what did we do? We took the area of one rectangle. Is everybody with me, right? We took the area of one rectangle, but then we added them all up. But let's just focus on the area of one rectangle. And how did we describe it? Is it coming back now a little bit? Little bit. How do we describe it? What was the bottom? How do you get the area? Is width times height, right? So what's the width? What symbol? Robert, what symbol? Do you remember what symbol we used? Caitlin, you got me a symbol? Delta x, right? We said it's a change in x. So we said the bottom or the width was delta x. And what did we say the height was? James, it is delta y. It is a change in y. But if we specifically are going to use, you got it, it is a change in y. But if we're going to do a reference, like put our rectangles so that they're going this way as opposed to sideways, if I'm going to put my rectangles this way along the x-axis, how high is each rectangle? Well, sometimes we use the left endpoint. Do you guys remember doing that with Professor Soltis? Some of you guys are Professor Bataki. Sometimes you had a left endpoint. Sometimes you had a right endpoint. Sometimes you had the midpoint. Do you guys remember doing all that? But you had some point, and where was the point? It was somewhere along my curve, and so the heights were all defined by f of x. You kind of remember this a little bit, right? So the area of each rectangle was what? It was f of x times delta x. So every single rectangle had an area of f of x times delta x. I'm just going back so we can compare, right? Are you with me, Tim, so far, right? And then what did we do to all these rectangles? We added up all those areas. So we summed them. This is where that whole idea of Riemann sum came. Now, I'm being real sloppy here because I'm summing all those rectangles. So I'm summing all those rectangles. Now, each rectangle is unique to each interval, so I would have a subscript I and I equals 1 to n, but I'm looking big picture here right now. I'm adding up all those rectangles, but I want to get an exact area. This is just approximate. So then what did I do? I took my, who said limit? Was that Derek? Did you say limit? Who said limit? What? Ben, you said limit, right? No, who said limit? Chris said limit, right? Zach said limit. Okay, so then we took the areas of all these rectangles, and what did we do to make it better exact? We did what to our rectangles? We shrunk them. Do you remember? We made these really skinny rectangles. So we took a limit as what goes to what? What did we do? We shrunk it. So what did we send to 0? If you want to make that super thin, are you with me? Zach, walk me through this. I'm putting you on the spot, but let's walk through this. On the spot. Nobody look at Zach right now. He's thinking. I'm just kidding. What are we making for the 0? The width. What is the width? It is A to B, but one specific rectangle is defined by the width being delta x, right? That's the width. And so we want it to shrink. So we're sending delta x to, delta x to 0. Thank you, Tomas. Thank you. We're sending delta x to 0. So we are taking a limit of the area of all the rectangles, and that gave us this, and you guys really don't care. To me, this is beautiful. This is the fundamental theorem of calculus and all this kind of good stuff, right? This is where we start talking about defining the basics of the integral. Delta x, hello, everybody keeps forgetting to put dx, d theta, dy, whatever on your paper. This is crucial. If you don't have widths that are shrinking to 0 in this limit, you can't even write an integral. You have to put that dx on the back end. It represents the widths of all those rectangles. Okay, guys? Yes?
This is not for polar curves.
It's not for polar curves. Correct. Because it's x's and y's. Good, Tomas. So now let's do it with polar curves. Are you with me? So we're going to do polar curves. Okay. Now, polar curves. Now, look at me. Watch. Polar curves are not defined by rectangles, are they?
No.
What are they defined by? I've got an r and a theta. Are you with me? They are. Tell me, say what you just said. Kind of. This is theta. This is, remember, r kind of stays constant, right? Because r has to stay constant. They are defined by these things right here. What are these things called? Do you guys know what these things are called? Wedges. Okay, wedges. Sectors. Have you heard of the word sector of a circle before? No, you haven't. But you see, it's a piece of pie. Are you with me? Okay, guys. So, I forgot to do this well. I'll tell you in a little bit when I give you the formula on Friday. Okay. So, these are sectors. Now, is the area of a sector the same as the area of a rectangle? Because when we're talking area, we're going to be dividing this up into mini sectors, and we're going to shrink those sectors down and make them super. So what we're doing is we're going to take sectors, individual sectors, and we're going to then shrink these sectors. Do you see? So the question becomes, all right, if this is based on rectangles and polar curves are based on sectors, then if I want to create an integral based on sectors, I have to know what the area formula is for an individual sector first. Nobody Googled it yet? Ooh, I figured somebody would have Googled it, but let's work through it. Are you ready to work, brains? All right, Dylan, are you ready? Now I'm coming back to you, okay? Tomas is not off the hook yet. Tomas is going to give me my integral when we get there. Are you ready? But, Dylan, here we go. So I have a question. Let's say I have a circle right here. Can you tell me, and I know this circle has a radius of r. Can you tell me the area of that circle? Why not? Did you say why not? Or why not? Let's tell me the area of that circle. Hannah, yeah, you can help him, or he knows. Pi r squared. Exactly, pi r squared. Thank you. Alrighty. So the area of the whole circle is pi r squared. So my question is, what's the area of a sector of the circle? is a fraction of a circle. Are you all with me, right? It's a fraction of a whole. Are you with me so far, right? So, for example, let's just go right here to this part. Let's just do something easy. Let's take a sector like this, which we know, what would the area of this green part be, Tomas? That would be what? 1/4 pi r squared. Are you with me? Good. Does that make sense? And what is my angle right here? My angle right here is actually pi over 2. But what I'm looking at is what is the fraction of pi over 2 to the whole way around my circle, which is 2 pi. Are you with me? So we're looking for, do you guys see what I'm saying? We're looking for a ratio. Are you with me? A proportionality. What is pi over 2 divided by 2 pi? Think about it. It's pi over 2 divide 2 pi. What are you guys doing to the bottom? You're flipping and multiplying. Do you not see that pi over 2 divided by 2 pi is just pi over 2 times 1 over 2 pi, right? We flip and multiply, which is just 1/4. Ooh, no, seriously. Do you see?
Yeah.
Does that make sense? So, if I don't have, Tim, are you with me? If I don't have pi over 2, but I have the angle theta instead, what's the area for that sector with theta? It's going to be not pi over 2, but it's going to be theta divided by 2 pi, right? Like James said, that gives me my proportion of my circle. Kevin, are you with me on that? So theta divided by 2 pi, if I want the area of a sector of a circle, I want the proportion of that circle, which is theta divided by 2 pi, times what? Times the area of a circle, pi r squared. Cancel that out for me, Tomas. What happens when I cancel this down? What's that give me? It gives me theta, or 1/2 theta r squared. Would you agree? The area for a sector of a circle is 1/2 theta r squared. Okay, that took a lot, but you guys see, I want you guys to see the beauty of where it's all coming from. Do you guys see where it's coming from? It's just coming from a fraction of a circle. And why a circle? Because everything that we do in polar is based on r's and thetas. Okay, so how did we do this area? We integrated rectangles. We found the area of the rectangle, and then we shrunk it. We shrunk them up by taking a limit as delta x goes to 0. So we're going to do the same thing for our sectors, right? So we are going to find the area of a sector, which is 1/2 theta r squared. But here's the thing. We want these sectors to shrink. So what do we want to change? We don't want them to like shorten in. We want the sector area to shrink down. So what are we going to do? We're going to change what? R or theta? Logan. Oh, if I change R, that means, well, that'll also shrink the area. 1,000% you are correct. You are 1,000% correct. If I shrink the R down, it will change it. But I specifically kind of want to make these wedges thinner and thinner and thinner and thinner and thinner. So I'm going to change theta. So actually, it's going to be delta theta r squared, right? Because I'm changing my theta. So my theta is what I want to shrink. And so if I was going to add up all these sectors and take a limit as delta theta goes to 0, and again, this is all fluff and this is just generalization, but I want you guys to see the big picture. Gavin and Max, are you with me? So let's get an integral here. Somebody write it down for me. Go ahead. You guys give me some brain power over there on that side of the room. It's going to be an integral, go ahead, of what? Think about it. So if as delta x goes to 0, this thing turns into this, what do you think this one's going to turn into? Max, you want to tell me? What do you think it's going to turn into? So f of x stayed f of x, but delta x, because we were shrinking it, made the sum with the dx, right? Yeah, so what do you think this is going to do when the delta goes to 0? It's going to become what? You want to guess?
0.
It is. Those are going to go to 0. 1,000% they will. Absolutely. Can you rewrite this into an integral for me? Or do you want Hunter to? Hunter, go for it, Hunter.
1/2 r squared to the
1/2 r squared, and delta theta, because I'm adding them all up and I'm shrinking them and I'm taking a limit, right? What goes on the back end, Max? What is going on the back end? Absolutely d theta. Okay, guys? So this is your area formula. This is what we're going to do to add up all those sectors. We're going to add individual sectors, 1/2 r squared, okay? But we're going to shrink them down, d theta. We're going to add them all up, which is the sum. Now, because this is theta, the limits are going to be theta values. So we tend to use alpha and beta instead of A and B. Some people use A and B still. I like to use alpha and beta because we tend to use Greek letters to designate angles. Are you with me? And these are angle values. So these are theta values. If you go online, and I don't have, yes, I do have, I didn't have it pulled up. But if you go online into Canvas, I have notes. You guys know I have notes for the whole course, right? And in Canvas, I have these beautiful notes that kind of walk through what we just walked through right here. So it walks us through the area of a polar region with the area of a sector, talking about how it's proportional, right, to the outer curve and all these good things with the eyes. And in the back end, you get the area formula that we just generated, which is the area of a polar curve is the integral from alpha to beta of 1/2 r squared d theta, okay? It's true in art class. It's true when you get into calculus 3. Okay, it's always true the area. That'll be your formula for integration, okay, with polar curves. 1/2 r squared d theta. Questions? Guys, see where it comes from? Is it different? It's a little different, right, because it's all based on circles instead of rectangles. So it's a little different to talk about when you talk about area. But you guys are like, oh my God, Tina, it's so hot in here. Let's just go home. All right, so we'll do 3 areas, one of which will work out all the way. The other 2 will set up only, okay? The other 2 will set up only. So this one we're going to work out all the way. The other 2 will set up only. The very first problem I have for us then. Are you ready? The very first problem I have for us is this one right here. So now that we've talked about slopes of tangent lines and equations of tangent lines, I want to go ahead and find the area inside one petal of the rose curve. The area inside one petal of that rose curve. R equals 2 cosine 3 theta. Did I write my formula? Oh, I didn't write my formula down. I need to make it nice and big. Okay, hang on. I need to make it nice and big. We've got the integral from alpha to beta of, Ethan, got it? Write it. Can you get it to me?
Alright, 1/2
1/2
r squared
r squared
beta. That's d
d theta. So it's 1/2 r squared d theta. R is itself a function of theta, so you could write it r theta squared, okay, but that is the formula for the area. Alrighty, write your integral down. I want one petal. I want one petal. So do as far as you can go. Write as far as you can go. Yes, sir. We'll talk about, you know what, skip the limits for now, guys. Skip the limits for now. Skip the limits for now. Yes, that is d theta, d theta, d theta, d theta, d theta, because theta is the angle and the angle's changing. So, guys, skip your limits for now. Skip your limits temporarily. And the area would be an integral. We're skipping limits temporarily. And what'd you guys put in here? Ty, tell me what you put inside. You put what? 1/2? Whoa. Slow down. I missed you then. You took out the pi over 6?
I took out the theta.
Yep, and you put the theta in because we don't want it specifically at any point. We just make sure theta's in there, always, okay? So it would be 1/2 2 cosine 3 theta, good, squared d theta. Are you guys good with that? So let's talk limits. Ideas. I'll tell you what, there's probably 4 different ways to do this. What are you thinking, John?
You just do like, I don't know, like pi over 2 to pi.
Can I do, let's check. Pi over 2 to pi. Well, hang on, let me pull up my Desmos friend. Let's check. Let's see what happens. Pi over 2 to pi. So, first of all, I want to come back over here and I want to remind everybody on Desmos, I don't know if you can see it, but on Desmos, just to remind everybody, up here on Desmos, right? On Desmos, Desmos will automatically give us this. And what does this mean? What does this tell me? Kind of. It does tell me a domain specifically.
To know how far you need to go to do the full picture.
How far I need to go all the way around. So, if I go pi over 2 to pi, maybe it works. Pi divided by 2 to not 12 pi to pi. Not quite, right? So, what, Gwen?
Could you do 0 to pi over 6?
Why would I do 0 to pi over 6?
Because that's where it crosses the pole.
Oh, because we found it crosses the pole in 3 places. We found that it crossed the pole absolutely at pi over 6. It does cross at pi over 2, doesn't it? It really does hit at pi over 2. Right? It hits at pi over 2. So it hits at pi over 6, it hits at pi over 2, and it hits at 5 pi over 6. So if we go from 0 to pi over 6, if we go from 0 to pi over 6, 0 to pi over 6, that'll give me that half right there. I bet you any money, because of symmetry, if I go from negative pi over 6 to plus pi over 6, it'll give me one of the petals. I bet you if I go from pi over 6 to pi over 2, check that, pi over 6 to pi over 2, it'll give me another petal. And I bet you pi over 2 to 5 pi over 6, gives me another petal, right? Do you see what's happening here, guys? So let's go back to your idea, Gwen, of 0 to pi over 6. It gives me how much of the curve? It gives me half of it, right? It'll give me this half. But I've got symmetry. So we could go from 0 to pi over 6. We could go from 0 to pi over 6 and do what to it? Just double it. Multiply it by 2. So we could do this. 0 to pi over 6 of 1/2 times cosine of 3 theta squared d theta. Or we could do what we just showed on Desmos. I'll just put a big or. We could take 2 and we could go from pi over 2 to 5 pi over 6 of the same thing, right? Or, just like we saw on Desmos, we could go 2 times pi over 6 to pi over 2. That gives me the petal down in quadrant 3. Do you guys see what I'm saying? Or, you know what else we could do? We could find the whole area for all 3 petals of this windmill or propeller of an airplane or whatever this is, right? Okay. Or we could find all 3 petals and divide by 3. How long would it take to go around for all 3 petals? Sorry, I see I have this up here and I'm changing all these things and I'm leaving this up here. How long does it take to go around all 3? It takes 0 to pi. Sorry, I was changing these and you guys couldn't see when I was changing them, but I hope it helped and made sense. So the other thing we could do is go from 0 to pi, which gives me the area of how many petals, Chris, if I go all the way around? 3, so I could take 1/3 of that, right? Do you guys see that at this point there are multiple ways to do our limits, Maddie?
Would you still get the 2 in front if you're going to do pi over 2 to 5 pi over 6?
No, because it gives you the whole thing. Did I put it to, oh my God, I did. Thank you for telling me that. Thank you so much. Thank you so much. You would not need that because it gave us the whole way. My apologies. Thank you so much. You got it. You understand it. 1,000%. Sorry, I didn't mean to confuse you. Did that confuse everybody? A little bit? Next time just say, Tina, you just confused me. Whoa, whoa, whoa. My brain is confused. Unless you guys are always confused. Oh, okay, so you won't know when I'm doing mistakes. Ha, ha, ha. Questions? How are you guys? Are we good with limits? Is it not hot in here? Are you guys not hot? Holy, I'm hot. Anthony, are you hot?
Okay.
Are you ready? Okay, guys, get me that area. I don't care which integral you use. I don't care which limits you use. I want you to evaluate this and get me an area for one petal of this polar curve. Oh, I didn't write that, did I? It's pi over 6, right? I messed that up. I should have written 0 to pi over 6, and I might have erased it, right? Because 0 to pi over 6 and double it. Yeah. Make sure you put pi over 6 in there. Okay, guys. I'm wandering. You can ask any question. Thanks, Zach. So, did you do it with my limits, or did you do your limits, or different limits?
I did the 0 to pi over 6.
Okay, good. That's what I started for you. There you go. I can finish that up while I'm walking around. Okay, guys. How are we? Tim, how are you? Oh, why don't you? Come on. Cosine squared. How do we integrate cosine squared? Zach, how did you integrate cosine squared? Okay, well, okay, if you can't even get the cosine squared, then we're in trouble. It's 1/2 r squared theta, right? I'm going to put this here. Laptop goes here as well. Yep.
Oh, you can't do it. Oh, I just had a flip.
We integrate cosine squared.
No.
How do we integrate cosine squared?
Do you know what I'm saying? Okay. Never mind, I do know how to get the cosine.
Yes, it is. Power reduction rule. Thank you very much. Power reduction rule.
I've never seen it.
What do you want me to do? Tim, you just said you can't do this. Okay. Okay.
How are you guys? How are you? Good? Yes, Ethan, how are you? Absolutely, and that's 1/6. Good. Now you keep going. You're good. You are 1,000% good. Keep going. This is sines and cosines. That's not good. That's odd. So if it's even, you have
Getting a point on all the tests on that one.
How's everybody? Zach is working it out for us. He is using the limits that I started with, which is 0 to pi over 6, and I messed that up. Oh, sorry. This one is a pi over 6 right here. You can put that pi over 6. Thank you. Yes, sir. Yes, it is. He got lucky because everything drops out to 0. Do me one more thing. I'll put pluses here because derivative of sine is cosine. Got it. Perfect. It all dropped out for you, so it was all good and perfect. Yes, Maddie. How are you, John? How are you?
So much fun.
Oh.
Pi over 3. Let me pull this up. Who's got questions? Like I said, with the washers. Washers are based on the circles, just like our polar curve area is based on circles. And washer method was pi, big R square minus little r square. So if I'm going to get the area outside of one shape but inside a different polar shape, I'm going to take an integral from alpha to beta of not 1/2 r squared, but 1/2 big R squared minus little r squared d theta. That's my area in between those curves. Yes. Robert, question. If I want to go to x's and y's, then it's r sine theta. Y is r sine theta. X is r cosine theta. Is that what you're thinking? You're thinking unit circle, right? Okay. I like that your brain is pulling all this stuff together. I do. But how are you guys? Do you see this setup? Now, what's the hardest part? James, go ahead. What question? Go ahead.
How can we take the full little r when a part of it's sticking out of our shape?
Yeah, I know. So what we have to do is we have to find our limits. We have to find our theta values. The first theta is right here when we get to this point. The second theta is when we go all the way around. Notice we have to be real careful. We can't go in between these because if I'm going in between these, then I'm getting an area in here. So I have to go here from alpha, and then I have to go all the way around, and I have to finish over here at beta. So I'll be integrating all the way around to beta. So the first job I have to do is figure out what alpha and beta are. Okay? So how could I get alpha and beta? What is happening at those 2 points right there where we're creating this shape? What's happening there? They're intersecting. And when they intersect, what do I do to find intersections? What do I do? Logan, I set the curve equal to each other. Can you guys set your curves equal to each other for me and tell me what my angles are? Set your curves equal to each other and tell me what my angles are, okay? Did you set them equal to me for me? Sure. Oh, yeah, set them equal. What's the one? 1 minus cosine theta. And what's the other one? 1/2. Set them equal to each other. Set them equal to each other. So to get intersection points, set your curves equal to each other. So big R equals little r. So let's see. Big R is 1 minus cosine theta. And little r is 1/2. And so we're setting them equal to each other. And so I think I have 1 minus 1/2 equals cosine theta. if I'm solving this correctly. So I am looking on my unit circle, right, or anywhere where all my values of cosine equal 1/2. Where does cosine equal 1/2? Gwen, at pi over 3 or 60 degrees, but we always use radians with calculus, right? And give me another one. 5 pi over 3. Absolutely. Pi over 3 and 5 pi over 3 are the two places where those angles. And so I would then say that the area then starts at the angle pi over 3, goes all the way around, and stops at 5 pi over 3. And then I take 1/2 times big R squared, which is 1 minus cosine theta squared, minus little r squared, which is 1/2 squared d theta. I don't need to work it out right now because I want you to set up one more before the end of class. So we won't work it out right now. We just want to set it up so that we have that set up. Okay? We'll practice a lot of working out. In fact, not a lot, but you have 6 problems to do for your homework on Friday. Just 6 area problems. Not a whole lot, but enough to hopefully give you set up. Does this make sense? Are you guys ready to try one on your own? Is there any questions? Allie, good? Yep, you're good. Chris, are you good? Kevin, are you good? You're good. Acacia, good? Last one. Ready, guys? We're almost done. Class is almost done for the day. Wednesday is almost over. Here we go. Set up the integral to find the area inside the circle. R equals 2 sine theta. And outside the circle, R equals 1. Your first job is to label the outside, label the inside, find the intersection points, label the outside, label the inside, find 2 intersection points that are right next to each other, and set up your integral. You do not need to evaluate. Or just, that's if it's off-centered. See how it's off-centered? If it's centered at the origin, that one is centered at the origin. I see what you said. R equals 1/2. You said, yeah, type it. R equals 1/2. So let's type R equals 3. I didn't put that. I should have put that as one of our curves that we did. How are you guys? Are you finding intersection points and are you setting up your integral? I want to see it. I want to see the integral. I want to see your setup. Set it up. It's your ticket out the door. If I see it and it's good, very close. Almost. Almost. That's at 60 degrees. But sine is 1/2 down at 30 degrees.
Oh, I had it backwards.
Yes, you did. Yes, you did. So fix it. Fix it. Let me see where your integral is.
So like when
Yes, you're good to go. Yes, you're good to go. Hang on, let me turn this off.
that's your